we will finish section 11.1 with two examples dealing with the monotonic sequence theorem. And just to remind you, a sequence is both if a sequence is both bounded and monotonic, okay, then we know that that sequence is convergent. So if you can prove that the sequence AN is bounded and monotonic, then right away you can conclude that that sequence is convergent. And just as a reminder, we say that a sequence is called bounded, right, if it's bounded from above and from below. Okay, so if there is a number such that the elements of that sequence cannot go below that number, that's the lower bound, and the upper bound means that there is a number such that any element of the sequence doesn't go above that point. And we say that the sequence is monotonic if it is either increasing or decreasing. Okay, so let's see how we're going to use this. The example is use the monotonic sequence theorem to show that the sequence AN is convergent. Okay, so let's do the first example. Let's define AN as 1 plus square root of 2 n over square root of n. Okay, now most of you hopefully know how to show that this sequence is convergent. How to do that? Well, simply by finding the limit of AN as n goes to infinity, and this is a very basic example. This is the limit of 1 plus square root of 2 square root of n over square root of n, and as we can see, the order of the numerator and the denominator is the same, so right away you should already know that the limit of this sequence is going to be square root of 2. So if you factor out square root of n, this is 1 over square root of n plus square root of 2 over square root of n. Now we can cancel this. This goes to 0 as n goes to infinity. So 0 plus square root of 2 is square root of 2. But that's not the point here. I want to practice, I want to show that AN is convergent. Now we know that AN is convergent. I want to show that AN is convergent using the monotonic sequence theorem. Okay, and to do that, I want to show that this sequence is bounded and it's monotonic. Okay, so in order to figure out if it's monotonic, we have to figure out whether it is increasing or decreasing. Okay, so let's just list a few terms here. How much is going to be A1? A1 is going to be 1 plus square root of 2. Okay, how much is going to be A2? A2 is going to be 1 plus, when n is 2, 2 times 2 is 4, so square root of 4 is 2, over square root of 2. A3 is equal to 1 plus square root of 6 over square root of 3, and so on and so on. Okay, so what do we know here? I know that I have a feeling that AN is decreasing, right? If you evaluate this, if you have a calculator here, you'll see that these values are going to decrease. Okay, but having this feeling for few terms is not enough. We also have to show this. So we want to show that the sequence is decreasing. Okay, so how to do that? One way to show that a sequence is decreasing is right away show that AN is greater or equal to AN plus 1. Okay, so let's write down what are we trying to prove. AN is 1 plus square root of 2n over square root of n. I want to show that it's greater than 1 plus square root of, how much is n plus 1? Well, instead of n, put n plus 1, so 2 times n plus 1 over square root of n plus 1. So I need to show this. We want to show this inequality. We want to show this inequality, okay? Okay, so I'll continue. Here I have 1 plus square root of 2n over square root of n greater or equal to 1 plus, just drop the parentheses in this root here, 2n plus 2 over square root of n plus 1. One more time, n stands for positive integer, so that means that every term here, both denominators, are going to be positive, so we can cross multiply, and then I have 1 times this square root is just square root of n plus 1 plus square root of 2n times n plus 1 greater or equal to square root of n times 1 is square root of n plus square root of 2n plus 2 times n. Let's drop the parentheses, have square root of n plus 1 plus square root of 2n squared plus 2n. We want to make sure that it's greater or equal to square root of n plus square root of, by dropping this parenthesis here, I get 2n squared, 2n times n is 2n squared, plus 2n. Look at this. From both sides of the inequality, I get the same expression, which means if you bring one of these expressions on the other side of the inequality, it's going to be the same expression with opposite sign, so we can just cancel those two. And now this, for every positive integer, is evident, and you can stop here. So you have shown that this inequality truly holds. If you square both sides, you get 1 plus 1 greater or equal to n. So for any positive integer n, n plus 1 is going to be greater than n. So if you go back, you can see that we have shown this inequality. We have shown that an is greater or equal than the next term for every n. This holds for every n, which means that this sequence we have shown that an is decreasing. Okay. Now there is another way how to show the same thing without using these inequalities, but this way that I'm going to show you does not hold for every type of sequence, okay? Luckily here we can use it. So you can define a function f of x is equal to 1 plus square root of 2x over square root of x. Okay, now compare this function with this sequence, right? This function is going to have the same values as this sequence when it's evaluated, when this function is being evaluated at the positive integers, right? So now what is my goal? My goal is to show that this function is decreasing, and if I show that this function is decreasing, it's going to decrease for every x, right? Which means that this function evaluated at positive integers is going to be also decreasing, and with that I'm going to show that this sequence is decreasing. And showing that this function is decreasing is something that we have done over and over in Cal 1. All we have to do is show that the first derivative is less than 0. Well, let's find the first derivative. Just use the quotient rule here. Square root of x squared. Derivative of 1 is 0. Derivative of square root of 2 square root of x is square root of 2 over 2 square root of x times the denominator square root of x minus, by the quotient rule, 1 plus square root of 2x times derivative of square root of x, which is 1 over 2 square root of x. And here I cancel these two terms. I get square root of 2 over 2 minus, drop the parentheses, 1 times 1 over 2 square root of x is 1 over 2 square root of x minus square root of 2 times square root of x over 2 square root of x. So you cancel square root of x and square root of x, and look what we have. Square root of 2 over 2 minus square root of 2 over 2 over x. Well, square root of 2 over 2 minus square root of 2 over 2 is 0. And finally, we get that f prime of x is equal to negative 1 over 2 square root of x over x, or minus 1 over 2 square root of x times x. And I want to know how this function behaves for positive x's. Why? Because ultimately I'm trying to figure out how this sequence behaves, and the sequence is evaluated at positive integers, right? So this is clearly less than 0 for positive values. When x is positive, this term is positive, square root of x is positive, we have positive numerator divided by positive denominator times negative 1, that makes the whole expression negative. So if you show that the function is, so the derivative of the function is less than 0, that's another way to show that the sequence is decreasing. Okay, so we have shown that the sequence is decreasing in two different ways. Okay, and now in order to finish this problem, I have to show that an is bounded. Okay, so we will show that an is bounded from above and below. An, look at this. Let me just conclude here one more time, just confirm that an is decreasing, which means it's monotonic, right? So this part of the numerator is always positive. The denominator is always positive. This ratio is always going to be positive, right? So every element of this sequence is greater or equal to 0. So there is a lower bound. 0 is the lower bound. Okay? And now I have to show that this sequence is bounded from above. How am I going to do that? Well, I have shown that the sequence n is decreasing for every n, starting from the first one. Okay? So I can show that n is going to be less or equal to an plus 1, and maybe that's going to be the easiest thing, but I also can show this is obviously less than 3. So you don't have to show the smallest upper bound. You just have to find an upper bound. So I will show that every element of the sequence an is less than 3, and we have to show this, which means that you have to prove in a way that this is true. Okay, so I need to show that 1 plus square root of 2n over square root of n is less than 3. Okay, so multiply both sides by square root of n. Is less than 3 square root of n, and bring this guy on this side. 1 is less than 3 square root of n minus square root of 2 times square root of n. Okay, finally we want to show that a 1 is less than square root of n times 3 minus square root of 2. And is this enough? Well, yes, this is enough. Why? Because this term here is greater than 1. 3 minus square root of 2 is greater than 1. Okay? And square root of n is greater or equal to 1. The smallest value that this sequence can have is 1, when n is 1, and then it just becomes greater and greater. So a number greater or equal to 1 times a number greater than 1 is definitely greater than 1. So we have shown this, right? So here you can say that we have shown that the sequence is bounded and monotonic, and hence it is convergent by the monotonic sequence theorem. And I want to do one more example, an example where I'm not going to be able to use this method to show the sequence is decreasing. Let's do for increasing. Actually, we don't know what is going to be its behavior yet. So part B, I want to apply the monotonic sequence theorem to 2 to the power n times 3 to the power n over n factorial. Now, of course, again, you should know, right, that n factorial goes much faster to infinity than this is 6 to the power n, right? So this limit eventually is going to go to 0 as n goes to infinity, and indeed this is going to be, this just proves that the sequence is convergent. But I want to use the monotonic sequence theorem just to practice how to show that this sequence is bounded and monotonic. Okay, so again, I don't know whether this sequence is convergent or increasing or decreasing, so let's just write down the first few terms. When n is 1, I have 2 to the power 1 is 2 times 3 to the power 1 is 3, 2 times 3 is 6 over 1 factorial, which is 1, so 6. A2 is 2 to the power 2 is 4, 4 times 9, that's 4 times 9 over 2, that is 18. So the sequence is increasing. A3 is 2 to the power 3, which is 8 over 3 factorial times 3 to the power 3, okay? So this is 2 to the power 3 times 3 to the power 3 over 2 times 3, which is 3 factorial, right? So we cancel this, and I have 2 to the power 2 is 4, 4 times 9, which is 36. Okay, obviously this sequence is increasing, right? A to the power 4 is 2 to the power 4 times 3 to the power 4 over 4 factorial, which is 2 to the power 4. Let's write that 2 times 2 times 2 times 2 times 3 to the power 4 over 4 factorial is 4 times 3 times 2. Okay, so you cancel this and this, cancel this and this, and here you have 3 to the power 3, which is 27, and then you cancel 2 times 2 and 4, so 3 to the power 3 is 27 times 2 is 54. Okay, and then a to the power 5 is equal to, the sequence is increasing, and the question is, why am I doing this? And I'm doing this because there is nothing smarter that I can do at 20 to 10 p.m. So I'm just gonna continue doing this, and this is approximately 64.8. Okay, and then the sixth term of the sequence is 2 to the power 6 times 3 to the power 6 over 6 factorial, which is equal to 2 to the power 5 times 3 to the power 5. So what is going on? I'm taking one exponent of 2 here, putting it aside. 2 times 2 to the power 5 is 2 to the power 6, and 3 times 3 to the power 5 is 3 to the power 6, and then I write 6 factorial as 5 factorial times 6, and then I cancel this. And what do I get? I get that the sixth term is the same as the fifth term. The sixth term after the simplification ends up being 2 to the power 5 times 3 to the power 5 over 5 factorial, which is approximately, or maybe equal, now I don't remember, maybe it's equal, sorry, to 64.8. Okay? And then I evaluated the seventh term, and the seventh term is approximately 55.54. So obviously, getting some kind of feeling from the first few terms can be extremely wrong, because I needed to evaluate 6 terms to check that something fishy is going on, because the sequence obviously was increasing. A1 is 6, 18, 36, 54, 64, and then it was the 64 term again, and then the sequence starts decreasing. And I'm not going to continue checking whether this is going to continue bouncing or just decreasing and so on and so on, I'm going to come back to the beginning and tell you how you should start looking at this sequence from the very start, right? How you should begin thinking about the sequence. Well, we already talked about the order of growth, right? And we said that n factorial goes to infinity much faster. That's how we evaluated this limit, right? So eventually this denominator is gonna pull. And when we talk about sequences, we never talk about what happens with the first 7 terms or 8 terms or 7 million terms. When we talk about sequences, we want to know what happens, as we say, at the tail of the sequence, as n goes to infinity. So as n goes to infinity, the denominator is going to take over and start bringing this sequence, it's going to take over, it's going to be much, much, much bigger, right? So we expect that the following term is going to be less than the previous term, or we're expecting that the sequence is decreasing. So right away, we want to show that the sequence is decreasing as n goes to infinity, right? Greater than. Okay. Okay, so now one thing that we have to be careful here is the fact that I cannot define a function. I cannot define a function that is going to follow the elements of the sequence because of the factorial. So whenever you see a factorial and you have to show that the sequence is increasing or decreasing, please be careful here. You really just need to compare these two terms, okay? Because we have not studied what is the derivative of n factorial, and we cannot study that because that n factorial is not a continuous function, okay? I cannot define x factorial and expect that that's going to be a continuous function. So here I have 2 to the power of n times 3 to the power of n over n factorial. I want to show that this is greater than 2 to the power n plus 1 times 3 to the power n plus 1 over n plus 1 factorial. And again, similarly like in the previous case, I'm just going to cancel everything that I can cancel. So on the left hand side there is nothing to be simplified, but on the right hand side I'm going to write 2n plus 1 as 2n times 2 times 3n times 3, and then n plus 1 factorial is n plus 1 times n factorial. So let's cancel the terms that can be cancelled, n factorial and n factorial, 2 to the power n and 2 to the power n, and 3 to the power n and 3 to the power n. And now I get that 1, I want to show that 1 is greater than 6 over n plus 1. And indeed this is correct. This is correct. Multiply both sides by n plus 1, get n plus 1 is greater than 6, or n is greater than 5, right? So we have shown that this sequence is decreasing after the 5th term, and that's exactly what happened, right? At the 6th term we had the same value, because when n is equal to 5 I get 64.8, right? And then with the next term it was the same term, so maybe here to be true I can put greater or equal, right? And from then on, when n is greater than 5, an is greater than an plus 1. So we have shown that an, the sequence, is decreasing. It's decreasing. Okay? For every n greater than 5. Okay. So we have shown that the sequence is greater than decreasing for every n greater than 5, and a5 is 64.8, right? One upper bound is going to be 65. So let me repeat that one more time. 64.8, right? After this value, the sequence starts decreasing, and it decreases for all the n's, all the way to infinity, right? That means that 64.8 is going to be an upper bound. Well, any number greater than 64.8 is also an upper bound, so I'd say you can write here 64.8, but I write 65. Okay, so that's the upper bound. Another thing that we can notice here is that the numerator is positive, the denominator is positive, so obviously an is greater than 0, which shows that the sequence is bounded, and this implies that by the monotonic sequence theorem, the sequence an is convergent.